Welcome to the supplement lecture of Lecture 13. Here we are going to show an interesting result that connects the Poisson random variable with a binomial random variable. In particular, the binomial random variable that we are going to look at will have a super large n, but then a fixed expected value np. So let's consider this scenario. Suppose that you are a manager of a convenience store which is going to serve the customers that are living nearby. And somehow, let us denote the number of these potential customers as n. We assume that each of these customers will visit your store independently with probability p each day. So in that case, the number of daily customers will be a random variable, x, such that it is a binomial random variable with parameter n and p. As a manager, you keep record of the number of customers that visit your store each day, so somehow you know about the value of expected of x. Unfortunately, you do not know the value of n. And can we still make some approximation or estimation of what is the probability of x is equal to r without knowing the value of n? Now, the following results tell us that we can actually do so. So let x, or with x a subscript of n, to be a binomial random variable with parameter np, such that n is very large, but np is going to be equal to a fixed constant mu. Now, for any value of r that is much smaller than n, the probability of x is equal to r will be equal to e to the power minus mu, mu to the power r divided by r factorial when n tends to infinity. And if we observe the bound on the right-hand side, this is exactly what you expect for a Poisson random variable with parameter mu. So what does that mean? So xn behaves like a Poisson random variable with small r compared with n. Okay, so we are going to show this theorem. But before we do so, let us introduce two inequalities that we are going to use. So the first one is e to the power x when it is multiplied by 1 minus x squared is less than or equal to 1 plus x. Now, to get this, we can factorize 1 minus x squared into 1 plus x and then 1 minus x. And since 1 minus x will be less than or equal to e to the power minus x, so we can replace this 1 minus x term by e to the power minus x. So after multiplying all the things together, we get the desired bound 1 plus x. Another inequality that we are going to use is 1 minus t to the power n will be greater than or equal to 1 minus nt. To get this, we can observe that 1 minus nt is actually the first two terms in the Taylor's expansion of 1 minus t to the power n. So 1 minus t to the power n is equal to 1 minus nt plus some error bound. And in that case, the resultant will be greater than or equal to 1 minus nt. So we are going to use these two inequalities in the simplification of the formulas later. Okay, what we are going to show is actually by brute force computation. We are going to get an upper bound for the value of probability of x is equal to r. And later, we are also going to get a lower bound for the probability of x is equal to r. And we will show that when n tends to infinity, the upper bound and the lower bound matches to the desired bound that we want. So in that case, we prove the result. So first of all, probability of x is equal to r can be computed exactly by n choose r multiplied by p to the power r multiplied by 1 minus p to the power n minus r, because it is a binomial random variable. Now n choose r is equal to n times n minus 1 times n minus 2 blah 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 divided by r factorial. And for the numerator, the terms are bounded by n times n times n times n and so on and so forth. So in that case, n choose r is less than or equal to n to the power r divided by r factorial. Now we keep p to the power r unchanged, and then 1 minus p to the power n minus r, we separate them into two parts, 1 minus p to the power n and 1 minus p to the power minus r. And then 1 minus p is less than or equal to e to the power minus p. So 1 minus p to the power n is less than or equal to e to the power minus np. And after that, we can collect the terms together so that nr, pr is combined into np to the power r. So this is what we obtain at this moment. Now consider the effect when n tends to infinity. If n tends to infinity, then n times p, as we have mentioned, it is equal to the parameter mu, and np to the power r now changes to mu to the power r. Divided by r factorial, we keep it. And then for the last term, this part, because as n tends to infinity, but np is still some fixed value, this means that p will automatically tends to 0. When p tends to 0, this is 1 minus 0, which is like 1. And then there are only constant number of 1s multiplying together. So it is equal to 1. So in that case, we get the upper bound of the probability of x is equal to r is less than or equal to e to the power minus mu, mu to the power r divided by r factorial. Okay, next, let us obtain a lower bound. So we use the same exact expression for p probability of x is equal to r, but this time instead of using nr divided by r factorial, we use n minus r plus 1 to the power r divided by r factorial. And then we are going to handle with this part. Now notice that here, originally, it is 1 minus p to the power n minus r. And then we are changing it to 1 minus p to the power n by multiplying a bunch of 1 minus p, so that we get a smaller result. So in that case, this is okay, right? And after that, what we are going to do here is, this is 1 minus p to the power n. So what is 1 minus p? So using the expression as we have before, so a long time ago, this page, so we will see that 1 minus p, so here we are plugging in x as minus p, 1 minus p will be greater than or equal to e to the power minus p multiplied by 1 minus p squared. So this is how we are going to do the replacement. E to the power minus p, 1 minus p squared, but then that to the power n. So e to the power minus np, 1 minus p squared to the power n. And then the next part is we move e to the power minus np here, and then we combine the terms n minus r plus 1 to the power r and pr to be something like this. And then finally, we have another bound for this one. So recall that 1 minus t to the power n is greater than or equal to 1 minus n times t. So this is how we are doing. So we get a lower bound like this. And as n tends to infinity, e to the power minus np becomes e to the power minus mu. N minus r plus 1 will become n, so that this is n times p, which is mu to the power r, divided by r factorial. And how about the last term? The last term will be equal to 1 minus p times np. This is np squared, right? P times np. P is a value which is going to be equal to 0 as n tends to the infinity, while n times p is going to be a fixed value, mu. So in that case, it is going to be equal to 1 minus 0 times mu, which is 1. So in that case, this term will be gone. So in that case, we get the lower bound like this. As we have seen or we have proven in the previous page, we get the upper bound of the same form. So as n tends to infinity, the probability of x is equal to r will be exactly equal to this term. And then we have proven our theorem. That's all for this supplement lecture. Thank you.